over the air in all of the controllers throughout the entire vehicle at a time when other cars were just starting to update software in only their infotainment units. And furthermore, we've had sophisticated, anonymized data logging and telemetry capabilities that allow us to understand how the fleet is doing, what customers are doing with it, and how it's responding in the field to that usage. These two capabilities combined, OTA updates and data insights, give us the ability to iterate quickly on our software and to maximize the amount that we learn and proceed and the progress that we make in every one of those iterations. We've used these capabilities to inform countless design decisions in both software and hardware.
Yeah, one example is that we were able to monitor and track the use of the sunroof in our cars and found that our customers never use their sunroof, so we made this easy decision to remove it.
Very barely, yeah. We haven't had sunroofs for a while. As another example, we are able to use our collision data to design our crash safety systems for what happens in the real world, far beyond what regulatory and consumer ratings tests prescribe. And then furthermore, we're able to use that data to recreate in simulation all of those crashes every single time we make a change to the vehicle's design or to the software that controls the airbags and other restraint systems. Here on this graph, the gray dots that show up first are specific crash tests that are prescribed by regulatory and consumer ratings agencies throughout the whole world. And the rest of the color that fills in around and on top of it, those represent the crashes that we've seen happen in the real world. Those are what we design for and what we test to.
Right. And last year, this data was used to change the algorithm for seatbelt tensioning to reduce injuries in the field, which was OTA to all of our cars.
Here are a few statistics that demonstrate how staggeringly quickly we gain new insights from the anonymized data that we've received from the fleet every day. Every day, 123 million miles driven, 1.9 million charge sessions, and those rates are only increasing as we deliver more and more cars into the world. As another example, we've analyzed patterns in the way the fleet drives and charges to optimally size battery packs for our next generations of vehicles. And you'll hear lots of other examples throughout the rest of the day about how we're using data to inform decisions in the product and in manufacturing. So you've heard a lot from Pete, Colin, and others about how important vertical integration is for us in hardware, but it's especially important for us in software. And this is extremely difficult from the way the rest of the traditional automotive supply chain is set up. In most situations, all the controllers in the car are delivered by different Tier 1 suppliers, whose software is written by Tier 2 suppliers, who farm some of that software out to different Tier 3 suppliers, and so on and so on. Making a change that spans multiple components takes months of coordination before any work can even start. And furthermore, integration of software in the server side with what's happening in our vehicles has always been a core part of our DNA and enables us to do things that nobody else can. Most engineers think about the vehicle as a complete, consolidated, fully contained system. But in the software team, we think about the system as including the vehicle as well as all of our back-end server-side applications and infrastructure and the resultant feedback loop from the entire fleet that informs all the decisions we make as an engineering team. For example, we recently released a feature in Model S and X that automatically, predictively adjusts and raises the suspension for ride comfort before the car hits a section of rough road. We do that by leveraging the fleet to generate a map of road roughness everywhere our cars drive. Sounds pretty simple, but requires coordination of software across a number of different components inside and outside of the car. The restraint control module, whose inertial measurement unit senses the road roughness, the autopilot computer, whose GPS module and localizer figure out where the car is in the world, our navigation server, which aggregates the anonymized telemetry from the fleet and annotates our map with things like updated speed limits, lane topology, and now, road roughness. The onboard navigation engine, which looks ahead of the route that the car is traveling on and determines whether things are about to get rough. And finally, the air suspension controller, which takes all of those factors into account and decides, continue